Good afternoon, guys. How are you? Okay, so, today I'm going to do a recap on quantum computing, what I covered last week, because it was only Godwin here, so I found it to be not relevant for me to continue talking about things that you have not understood. So I'm going to do a summary of last week and then just a brief intro to today's thing. So last week I talked about the state of a qubit, and before we go there, for most of you who are not there last week, it was an intro on quantum computing. So what is quantum computing? Quantum computing it's a new way of doing computation, and that is through use of quantum physics principles. So quantum computing is where a computer is in two states, that's between 0 and 1 at the same time. So when that occurs, the computer can perform different tasks that the classical computers cannot perform. So the classical computers are the known ones. So you can do a lot of things such as simulating nature, discovery of drugs, and artificial intelligence. So to start off, quantum computing, you must understand what a qubit is. So a qubit is the fundamental ground of quantum computing. If you understand what a qubit is, then you can understand for the whole system when there are very many qubits. So, a state of a qubit. Okay. So in classical computing, normal computers, we had a bit. The bit represented 0 or 1. So it was in only one of the states, 0 or 1. So it has limitations, more so to do with the nature of problems it can solve. There are certain things that classical computers cannot solve. So in quantum computing we have a qubit, and the qubits are the building blocks of quantum computing. So so this is the definition. You can note it down. So a qubit is a 2D vector space, and a qubit is a vector in a 2D complex vector space. Yeah, a qubit is a vector in a 2D complex vector space. Yeah. So it's a two-dimensional vector space, and it can be represented using complex numbers. So for this, we would have this. For a bit, we have this, and for a qubit, we have this representation. For the normal computers, we have 0 and 1. For a qubit, it would be 0 and 1 to represent this. So this symbol here is a Kate notation. And what the Kate notation means, yeah. So the Kate notation represents the state of a qubit. So this Kate 0 represents 0, and Kate 1 represents 1. So So what's a qubit? Like a qubit it's the simplest form of representing information in quantum computing. So it can be an atom, a photon, or an electron. But for now, that doesn't matter. So, for example, this we say that qubit is a 2D vector space, and it can be represented in complex numbers. So when you look at K0, you will have this is its representation. Okay. So this is in the vector form, and then so this is the representation. So to add on to that,
You have 5 minutes.
5 minutes, okay. So someone could ask, why is it necessary to have complex numbers in a 2D vector? So we are going to get there. But when we're dealing with quantum computers, we deal also with superposition. So superposition means it can be in two states at the same time, which the normal qubit can't, the normal bit can't. Superposition also means a linear combination. So when you have this, okay, you can see that we have represented these qubits by this graph. Okay, and it will look something like this. This would be the equation. So I'm just going to summarize all these things in 3 minutes. So this is the linear combination of the qubit. This is the set of the qubit represented on a graph. So classically, this would not be possible. This would not be possible. So what next? So we talked about superposition. So superposition is being in two states at one time, and we can see that we are represented by a graph. So we say we can have complex numbers. So this represents 0. Okay. And if we had a complex number, it would be represented as a coefficient of this. Okay, this alpha and beta. This represent the coefficients of the states. Yeah. So the amplitudes can be in complex numbers. It can even be 2, it can be 1. But it can also be complex. It can also be complex numbers. Yeah. So if we had a complex representation, it would look something like this. It's all the same thing. Even this, when it's represented, it looks something like this equation. So far we have got to understand that a qubit it's a vector representation. It's a 2D vector, and it can also be in complex numbers. Okay, so just to to wind up, there's what they call the normalization constraint, which says that the sum of the square of the absolute values of the coefficients is 1. The sum of the square of these amplitudes is 1. And that means that the total probability of the state of a qubit is always 1. It will always be 1. And that's important when you're measuring the states. So then lastly, this can be represented by an equation. The state of a qubit can be represented by an equation. So this can represent the state of a qubit. Yeah. So that's most of it for today. I decided to go through last week's thing because most of it. So I didn't want to talk about quantum gates before I finish, or before people understand this. So if I started with quantum gates and it was only